Fill out the attendance form when you have a second. Yeah.
I was wondering if we can go over 14 on something.
If you can tell me what that question is, sure.
It's find the volume of a described solid. The base of S is a circular disk with radius r, parallel cross sections perpendicular to the base or square.
Awesome. That's literally, yes, definitely. You asked the perfect question. So situations we have so we're going to do a couple of these problems where you have like the base being some region and perpendicular cross sections are squares or semicircles or equilateral triangles, which is the worst. So let's look at this first one. So we have, and always writing these up those kind of weird. So let me write it up. So here's our first problem. The base of a solid is a circular disk of radius r. And I encourage you to save these words, and we're thinking about it as lying in the xy plane. Cross sections perpendicular to it. Well, it actually doesn't matter. Perpendicular to the x-axis are squares. Whose side length is given by the constraints of the disk. That noise. It's terrible. So I'll say about this picture you don't really need to draw, but I'm going to draw it so you can see it. So here's what I would say about this. We have a circle. So this circular disk of radius r, that circle is the base of our solid. And then sticking up out of it into the third dimension are squares, which are not typically great to draw in this sort of perspective. So I'm going to label this and then point out that this little strip here, which is perpendicular to the x-axis, that strip is the side length of my square. But then the square is going to pop up out of the page into the third dimension, which again, this is not the best kind of perspective to draw from. So what we're going to do is we're going to tilt this. We're going to tilt the XY plane to be looking like it's flat. So we're going to rotate that y-axis back like that. So now here's our XY plane. Sorry, our XY plane. And now the circle that's our base, or sorry, the disk that's our base looks like this. Right, sitting flat on the ground, and then popping up out of it into the third dimension are squares. So this rectangular strip here is the base of our square, and here's the rest of it. So there's one of the squares. Now, we're going to actually do this for any point in the disk. So like if I drew another little perpendicular strip there, here's the square popping out of it. And here, same sort of deal. So you can see that if we keep doing this, we're going to get some volume where all of the slices have square shapes. What does the word say before length is given? Whose side length is given. So the side length is just that right there. So here's how I'm going to imagine doing this. Just like with the disk and washer method, well, similar to the disk and washer method, we're going to imagine adding up all the volumes of our slices. So let's start with the volume of a slice. So the volume of this slice is going to be the area of the slice It's not crossed out. It's just written poorly. It says, that says side right there. Side length. The volume of our slice here is the area of a square. Great, we know how to find the area of a square. It's just the side length squared times the thickness, which is a small change in x. Now, we need the variable or the area of the square to be in terms of the variable we're using, which is x. So we need to figure out a way to write this length in terms of x. So we need an equation that's going to relate x and y. So here's what we're going to do. We say, well, the equation of this circle is x squared plus y squared equal to r squared. That's the typical equation of a circle whose center at the origin, radius is r. And this point right here is the point x comma y. So the length of this strip is twice however high y is. The length is 2 times y, but then if we take this equation and solve for y, we can say that y squared is equal to r squared minus x squared, or that y is equal to the square root of r squared minus x squared. So that the length of the side of the square is really 2 times the square root of r squared minus x squared. Which then means that the volume of our slice is really going to be 2 times the square root of r squared minus x squared squared dx. That's the volume of the slice of one slab, I guess, right? It's a thick square. And then just like every other time we've done this thing, we've talked about the volume of a slice or the volume of a disc or the volume of a washer, we're going to quote unquote add up all the slices volumes by integrating. So of course I haven't left myself enough room here. The total volume we're going to get by quote unquote adding up all the slices. So we have to say, well, if we look at this here, this circle of radius r that goes as far right as the point r comma 0 and as far left as the point negative r comma 0, we're going to find the total volume by integrating from x equals negative r to x equals positive r, this volume of our slice. This 2 times the square root of r squared minus x squared squared dx. And typically for these problems, the setup is really the hard part. The integration is not like always super easy, but it's often going to be the easier part of the problem. So nicely here, this simplifies really well. 2 squared is 4. And the square root of r squared minus x squared squared is just r squared minus x squared. Which is great. I'm going to bring out the 4. Actually, I'm going to do 2 things here. I'm going to bring out the 4. And I'm also going to notice that r squared minus x squared is an even function. It's a downward opening parabola with some y-intercept of r squared. But it's definitely an even function, which means instead of writing it as the integral from negative r to r of r squared minus x squared, you could just as easily write it as 2 times the integral from 0 to r of r squared minus x squared. And the reason you would do this is it makes it just a little bit easier. But we'll do it both ways to see that they really are the same. So let's integrate. And we'll do this kind of both ways. So if we integrate this, you have to remember that r is just a constant, x is our variable. So the antiderivative of r squared is going to be r squared times x. And the antiderivative of x squared is going to be x cubed over 3 from negative r to r. We plug in, we get 4 times r squared times r is going to be r cubed, bless you, minus r cubed over 3, minus, we plug in the negative r, we get r squared times negative r, which is negative r cubed, and then minus a negative r cubed over 3 is going to be a plus r cubed over 3. This, by the way, is why I like doing that instead, because this part gets a little bit like dicey with the negatives being raised to power. So we'll see that we're going to get the same thing, but this is what we get. Simplifying this, we have 4 times r cubed plus r cubed is 2r cubed, and minus r cubed over 3 minus another r cubed over 3 is minus 2r cubed over 3. Which then ends up just being, let's see, this is going to be 6 r cubed over 3 minus 2r cubed over 3, so we get 4 times 4 r cubed over 3, which is 16 r cubed over 3. Oops, sorry, I'm way off there. Apologies. Or if you did this easier thing, it does, I feel like it is easier. You have 8 times, you integrate this, you get r squared x minus x cubed over 3 from 0 to r, and then it's a little bit nicer. You get 8 times r cubed minus r cubed over 3 minus 0, which is going to be 8 times 2/3 r cubed, which is exactly 16/3 r cubed, or 16 r cubed over 3. Oh, same answer. So the hard part here is definitely the setup. Let's look, well, before we do another example, are there questions about what we've done here? I'm definitely going to do at least 1 or 2 more examples. So this is like the other type of volume question. Typically in this class, either you're doing a volume of revolution, which is going to use the disk or the washer method, or you're doing a volume like this, where you've got some base region and you have either squares or circles or semicircles or triangles jutting up out of it. Okay, let's look at another example. I will freely admit I am bad at writing these questions. I am bad at describing the thing that we're with words. So I'll do my best. Let's see, do I have another example here? No, great, fine. So let's say we have the following setup. The base of our solid is the region bounded by y equal to 4 minus x squared and y equal to 0. Cross sections perpendicular to the y-axis, yeah, to the y-axis are, let's go semicircles. Let's find the volume. So what I really want to point out about this problem, like the previous problem, is you don't need to draw the 3D picture that I'm bad at. You really only need to draw the 2-dimensional region. So my 2-dimensional region is bounded by the parabola y equals 4 minus x squared and the line y equals 0. All of you should try to draw that right now. Doesn't have to be perfect, you just have to have a decent idea of what that region looks like. Give you 45 seconds. Here's the attendance form for those of you on Zoom. Definitely should be trying to draw it, as drawing the region is kind of the best way to help you figure out what's going on. Okay, so y equals 4 minus x squared. It's a downward opening parabola. It's got a y-intercept at 4. It's got x-intercept at plus or minus 2. I'm not really trying to do a perfect job of drawing it. I'm just trying to get a decent idea of, okay, that's what it looks like. And then y equals 0 is the x-axis, so I'm not actually going to draw it. It's already there. I'm just going to shade in my region. So I know, great, there's Whoops, went a little too far there. There's the region I've got. And then I'm also going to draw the cross section that they told me to draw. So cross sections perpendicular to the y-axis. So my cross section is looking like this. Are semicircles. So from that strip there, I'm going to have a semicircle where that's the diameter of my semicircle. So again, I don't think we need to draw this other picture, but I'm going to draw it so you can kind of get an idea here. If I tilt this back again, do I want to tilt it back that way? No, I really kind of want to draw it that way. I'm going to draw it so that it looks like this, where the x-axis is coming out at you like that, and there's the y-axis. So here's x, here's y, and here's my parabola. Ooh, okay, I've drawn better parabolas and like that, but okay. Hopefully you get the idea. And then here's my strip perpendicular to the y-axis. And then popping up out of that is a semicircle. So our job is to find the volume of that slice. And very generically, the volume of that slice is the area of my semicircle times the thickness of the slice, which is dy in this case. Bless you. If you sneeze, I don't say bless you, just know that I mean it. I'm just doing math. But so everyone, blessings upon all of your sneezes. Or Gesundheit, or whatever, like say, salut, whatever. So the area of a semicircle is 1/2 times pi r squared. And now I have to figure out what the radius actually is in terms of the variable I need to use. So in this case, there's our radius. Well, again, I'm thinking of this point here as the point x comma y. And in this case, the x coordinate is what's giving the radius, because x is how far we are from the axis y. So here my radius is equal to r, which is going to equal just whatever x is. Well, my equation is y equal to 4 minus x squared. So if I solve for x, I'm going to get x squared equal to 4 minus y, x equal to the square root of 4 minus y. Technically, it's plus or minus the square root of 4 minus y, but since I'm on the right side, it's the positive square root of 4 minus y. If we had to be on the left side, it'd be the negative square root of 4 minus y. So that's the radius of my semicircle, and that's what's going to get plugged in my radius right there. So the volume of my slice is going to be 1/2 times pi times the square root of 4 minus y squared dy. Which again is going to turn out pretty great. A lot of these things look like they're kind of start off awful because you've got weird square roots, but most of the time your area formula ends up squaring whatever thing you're jamming into it. So it ends up turning out relatively not terrible. Then to find the total volume, in fact, I want all of you to set up the integral for the total volume. Should be the integral from, you should figure out the limits of integration of all that. Give you half a minute here to figure out what my limits of integration should be. I know I didn't write them down. You can find them. The points I just plotted there might feel like they're helpful, but they're really not. I know I just did this and this. That's not helpful at all. Your limits of integration are definitely not -2 to 2. Okay. So when I'm finding my limits of integration, I'm looking at my strip and I'm asking if it's a horizontal strip like this, how low and how high can it go? It can go as low as 0. It can go as high as 4. I really think about it like sliding. Like I imagine the strip just sliding up and down. It can slide down as low as 0 and slide up as high as, excuse me, 4. Similarly, if we have a vertical strip, I think about how far left and right it can slide to find my limit of integration. So then this becomes not awful. So our volume is going to be the 1/2 pi comes out in front. We get the integral from 0 to 4 of 4 minus y. Doesn't really get much easier than that. We integrate, we get 1/2 pi times 4y minus y squared over 2 from 0 to 4. You plug in the 4, you get 16 minus 8, which is 8. So you end up with 1/2 pi times 8, which is 4 pi. Yes, normally I would have actually written that out, but since I was squeezing it in there, I just said what it was going to be. But I think you all can do that without too much issue. Should we do one more? I think we should.
How do you know if it goes from like R to negative R or from like 4 to 0?
So I'm not sure, like, you mean like how do I know if I'm going horizontally versus vertically?
Yeah, or like if you're going vertically, then is it always R to negative R?
Well, I mean, it depends. I mean, I would say it's always left to right. I wouldn't say it's specifically R negative R, but it just depends on what your shape is. So, but like here, we definitely weren't going -2 to 2 because our strip was horizontal like this. Now, actually, that's a really good question. If instead the problem was phrased as the cross sections being perpendicular to the x-axis, then we'd have a different setup. So actually, let's do that. Let's say we want to do the same base. So same base with y equals 4 minus x squared and y equals 0. But now the cross sections are going to be perpendicular to the x-axis. Oh, sorry about that. Thank you. And instead of being semicircles, they're going to be, I don't want to say this right, squares, but it's not that the cross-section part is the length of the side, squares whose diagonal is the length of the strip or the length of the cross-section. Okay. So, same region. With points -2, 0, 2, 0, 0, 4. But now our cross sections are perpendicular to the x-axis, so we have to draw a vertical strip like this. And then the idea is that that strip right there, that is the diagonal of a square that is popping actually up and down out of the shape, which is kind of weird to visualize. If we think about trying to draw it, again, I don't think it's super necessary to draw it, even though I've drawn it every time. Here's my same shape. Ooh, okay. My parabola is on the not the best. Forgive me. All right, and maybe the orientation here is not going to be excellent, but here's my vertical strip like this, and what we're saying is that's the diagonal of a square that's doing this. So here's like the top of, here's one side of the square, and here's the other bottom half of the square. That kind of makes sense, yeah. Right. So they specifically say out cross sections are perpendicular to the x-axis. So since I had to draw a vertical strip that is perpendicular to the x-axis, that's how we know. But yeah, for these types of problems, they're usually spelling out which axis the cross sections are perpendicular to. So there's my funky looking square. And just like the previous times, I'm trying to find the volume of my slice. And just like the first problem, the volume of our slice is going to be the area of a square times the thickness, which is the thickness dx or dy? You should write it down. Oh. It's all right, it happens. The thickness is dx. Right, and whenever your strip is vertical, it's always dx. Whenever your strip is horizontal, it's always dy. Because it's literally a tiny change in x, or if it's a horizontal strip, a tiny change in y. Which again is why it's good to draw the strip. Now the area of my square, well, I always like to start out generically with these types of problems, meaning I know the area of a square is just the length of the side squared. Which means I'm calling this side out here in space the length. Okay, well, let's actually draw the square down here. So here's the square I'm trying to find the area of. That's the length. That's the length. And the diagonal is actually the thing that's this. Right, so this length here is that length there. That's what I actually have to work with. So let's try and get our formula in terms of that, and then we'll figure out what that is. So I know the area of the square is length squared, but I also know from the Pythagorean theorem that L squared plus L squared is equal to D squared. So then 2 times L squared is equal to D squared, which means that L squared is just 1/2 D squared. It is kind of weird that I just keep introducing new variables for the sake of it, but it really is kind of how people usually do this. Like we're just like, I'm just gonna call this thing something at some name so that I can work with it in a way that makes sense. And then I'm gonna find D in terms of X. Here it's just the function. So this height here is just 4 minus x squared. If we go over to some point, x comma y, well, y is the height. So y is 4 minus x squared. So this is really just going to be 1/2 times 4 minus x squared squared. And again, I'll say it one more time. The height of this function is that diagonal, and we just figured out that the area of the square, which is the length squared, is equal to 1/2 the diagonal squared, which is 1/2 the 4 minus x squared. And that's what's going to get plugged in there. So then the total volume we're looking for is going to be the integral of my length squared. So 1/2 times 4 minus x squared times dx. How is that? How is it that it's a triangular shape? Well, so it's a triangular shape because it's really 2 triangles, right? It's the top triangle and the bottom triangle, right? Just like the square here is really, I'm gonna rotate this a second. Right, that square there is, oh yeah, the top triangle and the bottom triangle.
I
That's
guess
how
I can't really see how the parabola makes a triangle. If that
Say that
makes
one more time.
I guess I can't really see how the parabola makes a triangle.
So it's not that the parabola is making a triangle, it's that this strip here is the diagonal of the square. And then this is in 2 dimensions. And then over here in the 3rd dimension, you've got the square popping up out of the triangle, out of the parabola, sorry. That's what's going on, is that we're saying, okay, this length here is just the length of the diagonal, and then there's your square popping up out of it. And if you had a, yeah, I'm nervous to draw a smaller one. If you had a smaller one like here, you'd have a smaller square whose diagonal was that thing there. That's gonna look terrible. So that's why we're getting that. But it's really just based on, right, if in the previous problem, right, we got semicircles, right? We didn't have circles here, but we got semicircles because we were told that the cross sections were semicircles. And so we had this semicircular shape popping up out of the plane.
Oh, okay, thank you.
You're welcome. Limits of integration. We going up, down, or left, right? Left, right. So we're going as far left as -2, as far right as +2. Should we finish it? So I have to square this out. Okay, so this is going to be 1/2 times the integral from -2 to 2 of 16 minus 8x squared plus x to the fourth dx. Is that an even function? It is. And we know it's even because, well, this is an easy one in that it's a polynomial. And polynomials where all the powers are even functions. Kind of like y equals x squared or y equals x to the fourth. So we could definitely write this as just the integral from 0 to 2 of 16 minus 8x squared plus x to the fourth. What happened to the 1/2? It got multiplied by the 2 that I didn't write. And then you can finish the rest. I'll leave that one to you. Okay, so these ones are not my favorite. They're fine though. But I would say, well, actually, I feel like I saw Dajjal say in the class like the other day, like these ones were super important. I feel like I heard him say that. I personally don't think they're super important, but I'm also not the one writing your exam, so I guess you should be prepared. You should be prepared for everything, honestly. I mean, I know that doesn't sound wonderful, but that is maybe the reality of taking a math class at UC Davis, and their expectations are anything is fair game. So, question.
That on the critical quiz today, he said that we have to know the critical points for relatively strong. Why would you know that? Yeah.
That's a good question. We haven't talked about that, have we?
He was talking about like C-17A, like
Okay.
derivatives.
So I mean, yes, you should, so I will say the material from 17A is certainly not fair game, right? Like it's still stuff that you were expected to be aware of and learn. So you should still be able to find the critical values of a function of one variable. Which is how do we find the critical values of a function of one variable? We take the derivative and set it equal to 0. Or undefined, and then find those values. I'm wondering in what context he is talking about, but like, I'm wondering why he's saying that. Someone asked, where does the 8x squared come from? So when you multiply out 4 minus x squared, you have to FOIL it out, and you get 4 squared minus 2 times 4 times x squared plus x squared. So the middle term is that minus 8x squared there. But yeah, I don't know, Annika. I don't know why he's saying that, but yeah, I really don't know why he's saying that. But that doesn't mean we couldn't address it. So do I have something in mind there? Yeah, really, I'm just trying to imagine like, what have we done recently where you would need to use that, and nothing really comes to mind. That's all he said?
Yeah, he's talking about like, oh, like the quiz for tomorrow, like
Yeah.
survival renewal, volume,
In regard to rotations.
max and min, like absolute value from like a 17A.
Okay, someone wrote here, he mentioned it during lecture in regards to rotations. Let me look at one thing real quick. So I'm just curious, has he posted, like, cause he usually gives like a discussion sheet or something before the quiz? That might give us a clue. We should do more revolutions though, so we'll do that in a second. I just want to see if we're totally off base here. Or if I'm totally off base. I don't think you're off base. I'm just like imagining things. He also mentioned maxes, yeah. We're at discussion sheet which? 5? Find the antiderivative, prove the mean value theorem. Oh, okay. Okay, so the last question on the discussion sheet seems like it might be getting at the thing we were talking about here. So here's the last question. It's worth looking at. The plasma drug concentration of a new drug was modeled by the function. This is number 9 from discussion sheet 5. I'm going to write the pertinent information. So the plasma drug concentration of a new drug was modeled by the function C of t equal to 23 t e to the negative 2t, where t is measured in hours and C of t, the concentration is measured in milligrams per milliliter. What is the maximum drug concentration and when does it occur? So part A, what is the maximum concentration? And when does it occur? Okay, fair enough. So how do we find the maximum of a function or the minimum of a function? I should really say, how do we find the extremum of a function? We take the derivative and we set it equal to 0. Slash undefined, but I'll point out that this function's derivative will never be undefined, so we're not going to worry about that. So we're going to take the derivative c prime of t, and I'm going to view this as 23t times e to the negative 2t when I use the product rule. So the derivative of 23t is 23 times the other piece left alone, plus, then we switch it up and we leave the 23t alone. We multiply by the derivative of e to the negative 2t, which is e to the negative 2t times negative 2. And then we're going to set this equal to 0. And again, normally you would also try to find if the derivative was undefined somewhere, but since this function is never undefined, we're not going to worry about that. And then to solve this, you typically want to try to factor as much as possible. So what's something that can factor out from both of these pieces here? An easy thing. The e to the negative 2t. What's the other thing that's even maybe easier than e to the negative 2t? 23. In fact, we could have pulled out the 23 in the beginning, but we didn't want to. So we're going to factor out a 23 e to the negative 2t. And we're left with, from here, what are we left with? 1. And from here, we're left with a t and a negative 2. So we're going to get 23 e to the negative 2t times 1 minus 2t. And when you're trying to set this equal to 0, you set each factor equal to 0, but I'll remind you all that this 23 e to the negative 2t is never going to equal 0. Because e to the something is always positive. Think about the graph of e to the x. It's always positive. And just to make sure, I told you all the thing about your right hand with e to the x. No? My hand is not the best for this because I'm old. But right there on your right hand, there's a nice graph of e to the x. And right there, kind of over your thumb, is a nice graph of the natural log of x. It's kind of great. Make sure you look at your right hand, though. Most of you are right-handed. Put down your pencil or whatever you're writing with and look at your right hand. Be like, oh yeah, e to the x and natural log of x. Kind of cool. So, Grant taught me that, by the way. But again, back to the point, e to the something is never going to be 0. So we don't have to worry about that. We're just going to set that equal to 0. And we're going to get 1 minus 2t equal to 0, which means t is equal to positive 1/2. So that's the when, right? We actually answered the second question first, is that in half an hour, we're going to reach, well, we're going to reach a critical point. We don't actually know it's a maximum yet. It could be a minimum, or it could be neither. So if I was asking this question on a quiz and expecting people to do all the work I wanted to see, you would actually need to show me it's a maximum. And the way you show it's a maximum is by the first derivative test. So I'm going to, on my number line here, I've got my 1 critical point, 1/2. I've got my derivative. And then I'm going to pick a number on either side. So if I pick 0, this is where it's really useful to know the thing we just said. E to the anything is positive. E to the anything is positive. So if I plug in 0, e to the anything is positive, so that's positive. I plug in 0 here, 1 minus 0 is 1, and that's positive, and a positive times a positive is going to be positive over here. And if I pick a number larger than 1/2, like 1, 23 times e to the anything is positive, and then 1 minus 2 times 1 is 1 minus 2, which is negative, and a positive times negative is negative, meaning our original function, c of t, well, if the derivative is positive, the function was increasing. The derivative is negative, the function was decreasing. So we do indeed have a relative maximum at t equal to 1/2. So t equal to 1/2 does give us a maximum.
That'd be absolute or relative?
You don't, well, the question didn't ask, I don't think. It just said, what is the maximum drug concentration? If you're only, since this is our only critical value, there is a theorem that says if it's your only critical value, it's and its maximum, it is an absolute maximum. If you think about it, the function is always increasing on the left side and always decreasing on the right side. So it was increasing forever from the left, hit this maximum, and decreasing forever afterwards had to be the only maximum, it is the absolute maximum. As long as the function doesn't have any weird discontinuities. So yes, it's an absolute max. What is the absolute maximum? Or how would I find it? I take my critical point that gives us a maximum and plug it back into the original function. So the actual maximum value is going to be c of 1/2, which if we plug that in, you're going to get 23 times 1/2 times e to the negative 2 times 1/2, which I would probably rewrite as 23 halves times e to the negative 1, or 23 over 2e if you prefer. And I would not pull out a calculator to approximate that. I would just leave it as is, unless I was asked to get a decimal approximation. So I'm guessing this is what he means by you should be able to find a maximum or a minimum of function. There's a part 2 here. Unless, well, so I should say, questions about it? Yeah, you guys know you can ask questions. Part B, part 2, is more straightforward in that it says, calculate the integral from 0 to infinity of c of t. And explain its significance. Okay, so first of all, what does it mean when we integrate this thing? If you're integrating the concentration, you're essentially adding up all the concentrations times a little bit of time, and you're getting essentially the amounts, right? So you're saying, oh, there's going to be some amount of milligrams in this time interval, some amount of milligrams in this time interval, and you're adding up all those amounts of milligrams to get some total amount of milligrams. Curious about these units, though. Yeah. I guess that's fine. I don't love that, though. Sure. Okay. Yeah. I feel like there's a unit issue here, but we're not going to worry too much about it. So to calculate this, we're going to have to find the limit as b goes to infinity of the integral from 0 to b of our c of t function, which is 23t e to the negative 2t dt. You might notice this integral is going to require integration by parts. If you know me, you know I don't like doing integration by parts when I have a limit and limits of integration. So I'm going to do it off to the side. You say, great. Let's just do the indefinite integral of 23t e to the negative 2t dt. It is integration by parts. Fortunately, it's only one time. So we're going to get our u is going to be something, our dv is going to be something. You should take a quick second and figure out what you think your u and your dv should be. Give you 20 seconds. So in this case, our u should be 23t. Our dv should be the rest. Once you pick u, dv is the rest. Always, 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 always. So dv here is going to be e to the negative 2t dt. Our du is 23 dt. Our v is e to the negative 2t divided by negative 2. And so our integral becomes u times v, so 23t times e to the negative 2t divided by negative 2, minus the integral of v du, which is e to the negative 2t divided by negative 2 times 23 dt. And simplifying this just a bit, we're going to get negative 20. Ooh, so I'm going to do something that is going to help me do this problem. I know that I'm going to have to take the limit as something goes to infinity eventually. And I personally like having a positive infinity pop up. So instead of having e to the negative 2t in the numerator, I'm going to rewrite this as 23t over 2 times e to the positive 2t, because I find that more helpful. And then minus a minus is plus. I have a 23 over 2. And then the antiderivative of e to the negative 2t is e to the negative 2t divided by another negative 2. And the way to make this actually the easiest is to factor out the e to the negative 2t or the 1 over e to the 2t from the, well, actually, no, let me backtrack that immediately. The way to make this the easiest is to kind of write this as one fraction. So I'm going to write this as, yeah, I kind of shot myself in the foot by doing that first. Oh, well, sometimes you make mistakes. So I'm going to do negative 23t over 2 e to the 2t minus, because there's a minus sign there, 23 over 4 e to the 2t. And then I guess I'm going to multiply this first one by 2 over 2 and get negative 26t minus 23 all over 4e to the 2t. Normally, I would not care about this. I would just leave it as two pieces added together, subtract it, whatever. But I know that when we do this problem, we're going to have to use L'Hopital's rule. And I would rather only do it on one piece versus two pieces. So I do think if you have an improper integral like this, where you have to use integration by parts, and you have like some e to the t times t kind of stuff, it's probably worth your while to write this as one fraction. So let's see what we get. We did the integral. Now let's go back over here and be like, okay, we're going to plug it into this whole thing. This is going to be the limit as b goes to infinity. We just did the antiderivative of that. It's that. So it's going to be negative 26t minus 23 all over 4e to the 2t evaluated from 0 to b. Hopefully you can see why I chose to do all this on the side and then just plug the antiderivative back in here and then plug in b and 0 and then take a limit of that. I don't want to carry all of that machinery the whole way through. We plug in b, we get the limit as b goes to infinity of negative 26b minus 23 all over 4e to the 2b minus, then we plug in 0, we get negative 26 times 0 minus 23 all over 4e to the 2 times 0. Right here, this is an infinity over infinity type of limit. Specifically a negative infinity over infinity, not that it really matters which sign of infinity we have. But for this negative infinity over infinity limit, we can use L'Hopital's rule. In fact, we need to use L'Hopital's rule. So using L'Hopital's rule, we get the limit as b goes to infinity. The derivative of the top part is negative 26. The derivative of the bottom part is 4e to the 2b times 2. This part over here is just a constant. We're leaving it alone. We're not even really looking at it, but we are going to add it on. Like it's still, right? It doesn't just go away. Right? The L'Hopital's rule part is only really applying to this because there's no b's here to take the limit of. So over here, you're going to get minus a minus 23 is plus 23 over 4e to the 0. And finally, as b goes to infinity, 26 over e to the b is 26 over something infinite, which is going to go to 0. Which hopefully isn't too surprising as typically if you have something that's a linear function over some exponential function, the exponential function is growing much, much faster than the linear function up here. And then finally, this question asks the question there, but let me say one more thing and then I'll look at that. The question asks, what's the significance of this? Well, what it means is that if you the plasma, so basically saying that the plasma drug concentration, if you let this process, it doesn't really, I feel like the words here are not great. So if you basically let this process continue, although the process wasn't really described here, basically you're adding up all the concentrations and saying, if you let this, whatever's happening happen forever, the amount of plasma in the new drug, I guess, is going to tend towards 23/4 milligrams per milliliter. I think that's what you know what, he's got solutions here. Why don't we look at those? I'm curious now. Let's see what he says here at the very end here. So he says it's 23/4 milligrams per milliliter times hours. That seems, there's not a lot of words there. So yeah. Okay. Somebody asked, if I multiply both sides of the fraction by 2/2, shouldn't I have oh, you're right. I should. I blew it there. Shouldn't you have a -46 in the numerator? Yeah. Somehow I multiplied the 2 by the 3, but not by the 2. Apologies there. That's not a -26. That's the weirdest possible thing I could have gotten. Should be a -46. Sorry about that. So that should be a -46 there, a -46 there, a -46 there. Fortunately, it doesn't affect the actual outcome because that part still has a limit of 0. But thank you for saying that. If you see me doing something dumb like that, please speak up. I know I go fast. You're welcome to be like, hey James, I think you made a quick mistake. You don't have to like wait for me to call on you. You can say, hey James, you made an error. You know what happens. Okay. So I'm guessing this is what he means by you should be able to find where a function has a maximum or minimum. So we should still talk a little bit more about volume. And then we should, well, yeah, so I'm not going to see you till Tuesday, right? All right, so let's do one more volume thing, and then we should spend a few minutes talking at least about the beginning of differential equations, because that is certainly where we're going next. I had a volume one. Yeah, let's look at, so let me clarify real quickly. Have you had volume questions where you have to revolve around axes other than the X or the Y axis? Like all around like Y = 4 or X = 2. Cool. So let's do a couple of those because I do think they're worth looking at. So let's say we have the following. Do I want that region? Yeah. Yeah, do I want that one really? Sorry, I'm just like, sure. I don't want to suck, but yeah, sure, I'll suck. So let's say we have the following region. The region bounded by y = 1/x, y = the square root of x, and y = 4. And this is something that we should be able to draw relatively quickly. Not perfectly, just quickly. So, square root of x, usual shape. 1/x, usual shape. And y = 4, I'm going to make it a little bit lower than it probably would be. Y = 4 is going to be like right about there. And it should be not terrible to find the points of intersection here. This point is definitely going to be the point 1, 1. X is 1, 1/1 is 1, and the square root of 1 is 1. This point here is going to be the point, well, if I set 1/x = 4, x has to be 1/4. It'd be 1/4, 4. And this point here, y is 4, then x is gonna have to be 16. That's gonna be the point 16 comma 4. And then we want to take this region and revolve it around its axes. So we want to set up integrals for the volume we get when we revolve this region about and we'll start with the x-axis. So again, here's the region we're looking at. I'm going around the x-axis, I have to use a vertical strip. Or more generally, if I'm going around an axis, I have to use a strip that is perpendicular to that axis. Which is not going to be fun here, because our region has two different vertical strip sections. You have to break it up. So let me draw this region a little bit larger, just so we can get a better bead on it here. Here's my region, just kind of drawn largely. So we have to break it up right there at x equal to 1. So here's our strip with this section. And here is our strip for this section. My volume is going to be, well, I'm going to have one integral that goes from x equals 1/4 to x equals 1. And it's going to be pi times my large radius squared minus my little radius squared. And then for the other one here on the right, I'm going to have another integral that goes from x equals 1 to x equals 16. And it's going to be, again, the large radius squared minus the small radius squared. So for this first one, the large radius is y equals 4. The small radius is y equals 1/x. For this right one, the large radius is still y equals 4. The small radius is y equal to the square root of x. Maybe I should write this is y equals 4, y equals root x, y equals 1/x. But really, 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 I'm just using the picture to help me see what's what. And again, not again, I'm imagining, although I'm not, I really think this is all you have to draw. Right? You don't need to draw like the revolving around the axis part of it. What we're imagining, right, is that we're revolving this little strip around the x-axis and we're getting some sort of washer shape like this. But I don't really care to draw this. You shouldn't draw this unless you really, really, really want to. The important piece here is that we recognize that, oh yeah, there's our outer radius. There's our inner radius. Outer radius is just the difference between, I know what I want to say. So I want to say here is the outer radius is 4 minus 0. It's the difference between your function and the axis of rotation. And the inner radius is root x minus 0. Same deal over here. Outer radius is 4 minus 0, and inner radius is 1/x minus 0. So I didn't show the work. The way I got the balance was, so I'm really just setting the functions equal to each other. So like for this 1 right here, I'm setting 1/x equal to the square root of x. But honestly, I'm just saying, I know that if I plug in 1, it's a solution. So really, I would say I'm finding the balance by inspection. I'm guessing likely candidates as the answers because usually people are giving you regions where the numbers are relatively nice. But we can also solve this, right? You could say that, you could say that 1 equals x to the 1/2 times x, so that 1 equals x to the 3/2. And the only solution there is going to be x equal to 1. And then for this point here, same idea, I'm setting the square root of x equal to 4, and then I'm just squaring both sides. So x equals 16. And for this one here, I'm setting 1 over x equal to 4. I'm taking the reciprocal of both sides. Saying x over 1 equals 1 over 4. So x equals 1/4. So that's how I'm getting those points of intersection. Generally, we're getting the points of intersection by setting functions equal to each other and then finding the solutions.
And
Mhm.
you did like the left side and then you did the right side.
Right, and I had to break this up into 2 sections because, unfortunately, on the left side of 1, the top function is 4 and the bottom function is 1 over x. And on the right side, the top function is 4 and the bottom function is a different function, the square root of x. And so we're stuck, right? If we're going around the x-axis, we are absolutely required to use 2 intervals here. There is no other way to do it. That's not true. There's another way that we learned how to do it. Because there is a totally different way to do it, but we don't know that. Okay, let's see. Oh, go ahead.
Horizontal strips, right? So we have to do it over the x-axis.
Right. Right, our strips have to be perpendicular. As a quick aside, in a different calculus class, there's a thing called the shell method, where your strip could be parallel, but we don't learn the shell method here, so we are always forced to use a perpendicular strip. But in case you've had other calculus classes before and you've learned about the shell method, that's what you might be thinking of as if you could do it a different way, but we're not doing it that way. Okay, let's look at a different axis that is also horizontal, and we'll do 2 of these actually. So let's say whoa, geez, paper just sliding everywhere. So let's say we wanted to go around the line y equal to -2. So same region. Oh yeah. But now we're going around this axis down here. And here's how I really want you to conceptualize this. In fact, I am going to draw some pictures here. So for this strip here, right? I'm rotating that strip around that axis. So draw this out here. It's going to be a very, very big washer. Like a ring. You guys see that okay? I feel like the green doesn't show up that well. So my radius, both of my radii of both the larger radius and the smaller radius, both got bigger by 2. But the way I would encourage you to think about finding the radii here is that my outer radius, well, it's just the difference in the function and the axis of rotation. So the outer radius here is going to be the top function, which is y equal to 4 minus the axis of rotation, -2. And the inner radius here, which I drew kind of terribly here, is going to be the closer function, square root of x minus the axis of rotation, -2. So for this right-hand part, the volume is going to be the integral from 1 to 16 still. But now my outer radius is, I'm going to draw this again. Sorry, I didn't leave myself enough room there. Let's just write it down here. So for this right-hand part, which is the integral from 1 to 16, my outer radius is 4 minus -2, and then we're squaring it. And my inner radius is square root of x minus -2, and then we're squaring it. And then we're multiplying it all by pi. So there's your pi times your outer radius squared minus your inner radius squared. That's for the right-hand side. And then for this other left-hand side, we're going to do the same thing. We're going to do the integral from 1/4 to 1. My outer radius is still going to be 4 minus -2. And then we're squaring it. My inner radius now is going to be the distance from my closer function to my axis of rotation. So it's going to be 1 over x minus minus 2. And we're squaring it. Don't forget the dx and the pi. Yes, I'm aware that 4 minus minus 2 is equal to 6. But I'm writing it this way to emphasize the fact that the radius is the difference between the function and the axis of rotation. In each of these cases, function minus axis of rotation, function minus axis of rotation, function minus axis of rotation, function minus axis of rotation. Just like in the previous one, I was talking about how you could think of the radius as being your function minus 0. We just don't write them. Yeah.
And then you split up, like it's kind of.
Well, so this one's being split up because again, right, if I draw a vertical strip, depending on where I draw the vertical strip, the bottom function changes. So right here at 1, I have to change from being the inner radius being the square root of, sorry, the 1 over x minus minus 2 to over here being the square root of x minus minus 2. Because you have a different lower bound of your strip. We'll see that not be the case when we do it around the y-axis in just a minute. So let's do one more like this, which is going to be, there's just one more thing I want to point out. Yeah, I do. So what if instead we went around the line like y equals 6? Well, now it's the same sort of deal. After same region here. But now we're going around this line here. And so which things get to play the role of the outer and the inner radius actually change. So this is why it's really, really good to have the picture. Because you have the picture, you can look at it and say, okay, well, I'm still going to break this up at 1. If we look here now, for this left-hand side, the outer radius is the distance from your axis to the further away function. And the inner radius is the distance from your axis to the closer function. So for the left-hand part here, the volume is going to be the integral, still from 1/4 to 1. My outer radius squared is going to be, that's the function 1 over x. It's going to be 6 minus 1 over x quantity squared. Because it should be the bigger thing minus the smaller thing. Minus, then the inner radius is going to be 6 minus positive 4 squared. So that's the volume of this part being revolved around here. And then we have to add on the other part. So for the other part, I don't like the green. There's my outer radius. There's my inner radius. My outer radius is going to be 6 minus the square root of x squared. And my inner radius is 6 minus 4. And then we're squaring it. This is why the picture is really, really useful because it helps you see which function is playing the role of the outer radius, and it can change depending on where your axis of rotation is. But the outer radius is always just the function, or I should say, the outer radius is always just the difference between the function that is further away and the axis of rotation. And the inner radius is always the difference between the function that is closer and the axis of rotation.
So in this case with y equals 6, since that was above the shape, if I were
Yes.
adding 6?
Well, we're doing 6 minus. It's always the difference, right? So when I'm finding this axis of this radius here, it's the difference between my axis of rotation and my function that's further away. And when I say difference, the mathematical operation that gives me that is subtraction. So it's 6 minus 1 over x. Just like in the previous one, it was the square root of x minus minus 2. Yes, that ends up making the radius 2 larger. You could certainly write that as the square root of x plus 2. but I want you to think of it as finding the difference between your function and the axis of rotation. I know in class, when he did a problem like this, he did just say it was +2 because you were making the radius too bigger, but it's more generically nice to think of it all as the difference. It's going to work every time if you think of it as a difference. So when you're finding the radii here, it's always the difference between your axis of rotation and your function. And the order you subtract just depends on which one's bigger. Here, the axis of rotation is bigger, so we do that minus our function. Whereas down here, the axis of rotation was smaller, so we did our function minus the axis of rotation. And technically, if you did it in the wrong order, it would be okay because you're squaring it, and a negative number squared is going to turn out positive anyway. But you should subtract in the right order. But if you subtract in the wrong order and then squared it, it would actually turn out fine. Okay, we have 6 minutes. Let's talk about going around the y-axis. I know I'm sick of this region, but what we've got. Here's our region again. I'm gonna label the points again. That's 1/4, 4. That's gonna be 1, 1. That's 16, 4. Functions, in case you've forgotten them, y = √x, y = 4, and y = 1/x. Now, if we're going around the y-axis, we're going to use a horizontal strip. Again, our strip must be perpendicular to the axis of rotation. And here, we're only going to have to use one interval because no matter where you draw the horizontal strip, the right function is always y = √x, and the left function is always y = 1/x. So, if we revolve this around the y-axis, again, you don't need to draw this part, but I like drawing it. There's my washer. And the volume of my washer is going to be pi times large radius squared minus pi times little radius squared times dy. Oh, that dy tells me that my functions better be functions of y. So it's not going to be, we are not going to write pi times the square root of x squared minus pi times 1/x squared dy. That's not going to help us. We have to change those functions to functions of y. So instead of writing y = √x, we're going to square both sides and get y squared equal to x, or x equal to y squared. And instead of doing y equal to 1/x, we're going to solve for x. We're going to get x times y equal to 1, or x equal to 1/y. We're going to use that. So really, the volume of our washer here is going to be pi times y squared minus pi times 1/y squared dy. And then the total volume is going to be the integral, not from 1/4 to 16, but from 1 to 4 of pi times our outer radius squared minus our inner radius squared. Okay. Do I really want to draw this picture again? No. Let's see if we can fit in down here. One more. I know it's a lot. We can do one more. What if we want to go around? I didn't even write this here, around the y-axis. What if we want to go around the line x equal to 20? I should do a new picture. I got 3 minutes. I can draw a new picture. Okay, so same region. There's my horizontal strip again. And looking at this, here's my inner radius. There's my outer radius. labeling things because we should label them. I mean, you don't really have to label them. I'm just labeling them so you can see this. So my outer radius is going to be x equals 20 minus x equals 1 over y. Or more succinctly written, 20 minus 1 over y. My inner radius is going to be x equals 20 minus x equals y squared. I do like writing it like this because I'm like, oh yeah, I'm subtracting an x equals thing minus an x equals thing, which end up being y things. And that's kind of weird. So the volume here is going to be the integral from y equals 0 to y equals 4 of pi times my outer radius squared minus my inner radius squared. So I think the main point of everything I've just said about volumes just now is that when you're finding the radius, it's always the difference between your axis of rotation and your function. And the order of subtraction is just the bigger thing minus the smaller thing. So if your axis of rotation is to the right of your region, it's your axis minus the stuff. If your axis of rotation is above your region, it's your axis minus the stuff. But if your axis is below the region, it's your stuff minus the axis. Or if I had drawn another one where my axis was to the left of the region, then my radii would be my stuff minus the axis. So that's how you're finding your radii, is you're just finding the difference. You are subtracting your function minus the axis or your axis minus the function. That's all I got. I guess we won't talk about differential equations today. Next time.